Right, welcome to tutorial 2. Today is the 8th of September. So basically what we are going to do is question 7 today for tutorial 2. And then as well as question number 8. And then if we have time, we'll go back to do question 6. All these videos have been recorded, so we have put it into YouTube, at least for tutorial 2, question 1 to 5, and question 6. So let's begin to solve for question 7. So the first thing first, we've been solving this problem since the first tutorial. The problem is to find x such that ax is equals to b. And typically we are given the A, the matrix 3 by 3, and we're given the B, 3 by 1, and then the vector x is 3 by 1. And then if there is a solution, means that we have find the x that will solve this equation ax equals to b. And of course, our approach since day one was to do Gaussian elimination. And then followed by, in the Gaussian elimination, we have the matrix in this form. And then what we do is that we keep on row reduce to get into a triangle form like this, where the square represents the pivot, x represents any number, and then of course what we typically do is that we have the b here, which is 0, minus 5, and 7, and this is the augmented matrix. And then we have the augmented matrix here. Let's call it b prime. Now, so we know how to do this by Gaussian elimination, and then we realize that once we have it in this form, we can solve for x3, we can solve for x2, and we can solve for x1 from the back. So this is called back substitution. Now, we could do back substitution because the matrix of A has been reduced to, in this case, it looks like this, guys, an upper triangle. And in the upper triangle, we start from the bottom first to perform the back substitution to solve for the variable. So you realize that we like this upper triangle. We like the upper triangle because it allows us to solve for the variables x1, x2, x3 very easily. We solve them one at a time from the back. x3 followed by x2 and then x1. Now, so we're going to see this upper triangle again in something called an LU factorization. Okay, so what does the LU factorization do first? And we come back to the problem. LU. Basically, LU is an operation that takes the matrix X in MATLAB and will give you two matrices, one called L and one called U. And this matrix together, when they multiply, is A. So how do I know this? So I'm going to take this guy away first. So I type the matrix L first. This matrix L is this matrix L. Oh, sorry. So 1, 0, 0, 0.5 for second row, 1, 0, 1.5, minus 5, 1. So this is the L matrix. We also have the U matrix. So the U matrix is the upper triangle matrix. So I've also typed here U, 2 minus 2, 4, 0 minus 2, minus 1, 0, 0 minus 6. So it says that L times U will give you A. So let's multiply this. So I've typed L, now I have typed U. So L and U are there. L times U is equals to A, which is 2 minus 2, 4, 1 minus 3, 1, 3, 7, 5. So it shows that a matrix A can be decomposed into two matrices. One called a lower triangle because it looks like this. Let me erase some of these first to get rid of. So it looks like a lower triangle. And here, the other guy looks like upper triangle. So that's why the name L and U, lower triangle and upper triangle. How we get these two triangles is not our problem today. We say that we know L and U of A. And then he asks us, let's solve for X. So it begins like this. AX equals to B. And we are given A is LU times X equals to B. So we did nothing except substituting LU to represent our matrix A. And then now what's the big idea here? Well, we can open up the bracket because you remember that we can do any way we want first because matrix multiplication, L times U times X, matrix and vector multiplication is associative. Associative, as you remember, means A times B times C is equals to A times B first times C is equals to A times B times C. Whichever way you do it is fine. So what's the big idea? The big idea is that you realize that if we do Gaussian elimination on this guy and we are drawing the augmented matrix, then this operation is actually quite expensive for every different B. Instead, if we do LU, we can save something interesting. So how do we save it? We are going to do it this way. So I'm going to call this Y first. So let's Ly equals to B. So what we do is that the first step is to solve for Y. And to solve for Y, what we do is instead of doing A and B, we are doing it L and B. And then this will solve for Y. So why do we do that? Because once we have solved for Y, remember what is Y? Y is equals to UX. And instead of writing it this way, I should actually have written it like soft Y. Now UX equals to Y. And now we can solve X. And then we are done. So you'll be wondering, why did we go from a very easy problem of Gaussian elimination using AX equals to B, and then now break the problem into two steps? Okay, so maybe I should use this slide to show you. The key idea is this. When we do when we solve for Y, what you realize is that we basically fix L, and for different B's, it's very easy because L is a triangle, right? So this is L. This is B. And when we perform this, we are doing nothing but what do you call that? Forward substitution. And the reason we say forward substitution is because we are using the variable first to solve for this. And what are we solving? We are solving y1, y2, y3 in our example of a 3-variable problem. Now, once we have solved for y, then we can solve for ux equals to y. And what is ux? Ux is the upper triangle, and this is our y. So basically, once we have solved for the y, we put it here, and now this is our u. And this is very easy because, again, we do, now this is back substitution, backward, because we start from the bottom. Compared to the top, is forward substitution, is a back substitution. Okay, and then, of course, the whole idea is that in the backward substitution, we have finished solving for x, and we are solved. And the reason why we use LU factorization is this. It is because LU decomposition is actually a very, what do you call that, efficient method, especially when we are repeatedly solving for the equation on the same left-hand side, which is the A, but on the right-hand side, we have keep on changing different B. So the A is fixed, but B is not. Now, if A is fixed, then what happens is that if we perform LU decomposition, it is a much more efficient method. Okay, so now you understand the rationale behind LU decomposition of solving this. So let's go back to our problem. Okay. So to do the problem, maybe I would go through at least the numbers. Now, what am I going to do? Let's just name the few steps. First is AX equals to B. The second step, we let LU be A. So it's LUX equals to B. So nothing has changed. We let UX equals to Y. The third step is LY equals to B. And then the fourth step is solve for Y. So now how do we solve for Y? Well, what we do, we have L. This is L and this is U. So we are now going to write L, the matrix, 1 half 3 over 2, 0, 1 minus 5, 0, 0, 1. And we are solving for Y. On the right hand side is still B, which is 0 minus 5, 7. Now, so what do we do? How do we solve for Y? Please remember that this is the equation is doing Ly equals to B. Solve for Y. We solve from the third row, which is, we start from the first row, which is y1 is equals to 0, because we immediately can see this equation is nothing but y1 plus y2, 0 y2 plus 0 y3 is equals to 0. All right, what about the second equation? Let's change a different color. Orange, yep, okay. So this is half y1 plus y2 plus 0y3 equals to minus 5. And then we substitute y1 equals to 0 here. So y2 is equals to minus 5. Now we do the third one. Let's do it in blue. And the third equation is 3 over 2 y1. y1 is 0 now. Minus 5 y2. y2 is minus 5. Plus 1 y3 is equals to 7. So what do we have? 1 y3 is equals to 7 minus 25, which is equals to minus 18. Therefore, y is equals to y1, y2, y3. So the vector y is equals to 0, minus 5, and minus 18. So we have solved for y. So we have found y. All right, the fifth step, sorry. Ux equals to y. Because the whole idea was to find x. What is u? Well, let's go and look up. So I must copy u first. 2, 0, 0, minus 2, minus 2, 0, 4, minus 1, minus 6. And we put a dash line. And now, right hand side is not b, it's y. So it's, I should change the color. And it goes 0, minus 5, minus 18. And then now we do back substitution because we can do the back first. So it is minus 6. And now we are solving for u x1, x2, x3 is equals to y, 0, minus 5, minus 18. So what are we doing? So it's the bottom goes from minus 6x3 equals to minus 18, implying x3 equals to 3. And then we solve for the second row. Oops. Okay, so it's minus 2 x2 minus x3 equals to minus 5. Therefore, x2 equals to minus 2 x2 minus 5 plus 3 minus 2. Did I make a mistake? Oops. Minus 5 plus 3. Okay, that's correct. Plus 1. And then you can solve for the last equation. Therefore, x1, and you solve it by yourself. And my answer is minus 5. Therefore, implying x1, x2, x3 is equals to minus 5 plus 1 and 3. So for sanity check, we always plug in this value and then into this equation here to see that a multiplied by this x will be really equals to b. Okay, so let's have a sanity check. And I use MATLAB, but you guys should use Python. And then let's just key in the numbers here. Okay, so L times U times X is minus 5, 1, and 3 transpose, and the answer is 0, minus 5, 7, and that is the correct answer. Okay, so we check it out and we are fine with this question number 7. Any questions so far? Okay, great. So this is question number 7. I guess from your perspective, LU is the first factorization, and there are many factorization. Given a matrix A, we can do LU, and in this is question number 7, and question number 8, it is, let's pick PDP minus 1. PDP minus 1 in question 8. So you realize that one of the key linear algebra problems is to break the original matrix A into very special matrices, and in LU it looks like a triangle, and in the question 8, this is actually eigenvalue decomposition. It breaks it into the left hand side is one matrix, and the right hand side is an inverse matrix, and D is a diagonal matrix typically. Okay, or not typically, it is. So in question 7 and question 8, we see that we can break matrices into smaller parts, and these smaller parts allow us to be very effective in solving some equations. So question 7 solve for ax equals to b problem. Question 8 is going to solve for a kx problem, where we realize that we are going to multiply a many times. Okay, so if you're okay, I'm going to proceed on to question 8. Any questions so far? Anyone want to clarify anything? Okay, right. All right, let's push. Now, first, we are given a square matrix A, and we say that this matrix amidst means can do, can be broken into PDP minus 1. And P is invertible because on the right hand side, you already see that he tells you that P minus 1 exists. D is diagonal. So the word D, yeah, is hinting that it's a diagonal matrix. Diagonal matrix means that only the diagonal elements are non-zero. Outside the diagonal is all zero. And then he says that let's find a square and a cube. Okay, using some clever idea. Because the most basic thing is that you would have done it this way, a multiplied by a. And then a multiplied by a is actually a very expensive operation because every element of a square is what do you call it? A row of 3 elements multiplied by another 3 elements. So every element is a n square operation because you have n elements on the row and n element of the columns. So is it n square? Is n times is one element times the other element plus one element and the other element. So it's very expensive. And imagine that you have to do 1,000 of them. And then, so this is horrendously expensive and you don't want to do this. Right, so what's the clever way? So if you ever can break the matrix into this form, then there's a clever way. Okay, let's see how. All right, but let's motivate first, okay? So we say A can be broken into P, D, P minus 1. We don't care what P and P minus 1 is, but all we know is that they are invertible. So what about A times A? So I'm going to write it in 2 different colors. The first A, sorry, the first A, I will still write it as, so I'm going to write the first A. I'm going to write PDP here. The second A, I'm going to write in green. So you guys can see. So the first A is in red. The second A is in green. So everyone's happy so far, right? Okay, and then now we have, of course, this is A square. And remember that, and always we will use this rule, which is matrix multiplication is associative, and we throw away the bracket. So I'm going to throw away the bracket in the middle. Oops. And then what do we do? Wow, we see that we have this nice 2 matrix P minus 1 times P. So remember P minus 1 times P is I, the identity, because P minus 1 is the inverse of P. And whether we have P times P minus 1, we still have the identity. Okay, so this guy reduced to identity. So then, what about D times D, guys? So let's try D times D. D times D, of course, is D square. But what's so special about D? D is a a diagonal. So let's study a diagonal carefully. Let's do ABC times ABC. What do you have? You have the row of A00 multiplied by the column of A00, you'll get A square. Then you have A00 multiplied by the second column, you'll have 0. Then you realize that because this is a diagonal, a diagonal matrix, when you multiply by his diagonal, is very easy because all we get is the diagonal elements square. Okay, so this is what we are after. We are after P dd P minus 1 P d square P minus 1, and we have seen that, oh, the diagonal is easy. All right, the diagonal is nothing but equals to, yeah, this guy. Okay. Now, so at least we know how to do it for a square. What about a cube, guys? So let's try for a cube. But maybe you already see the idea. A cube is equals to a times a times a. And this time I'm going to use the same color. We already can do this. Basically, then we do this. And now, of course, the magic happens again, which is that this guy reduces to I. And then now we have the same effect. P d times d square, P minus 1, P d cube, P minus 1. And then now we know that d cube is equals to A cube, B cube, C cube in this idea again. Okay, so to generalize, then AK equals to P dk P minus 1. Clear? All right. So therefore, then we look back at the question again. So now we find a square, we find a cube, we find ak, and we realize that this is the answer. Okay. Right. Maybe I should write it properly. P, and our question, of course, is the diagonal given to us is 1. The second element is half. The third element is 1/3. And the zeros are here. And then what should we do for the k is that we should bracket it together, and we have k here, we have k here, and we have k here for a k. So this is the k. All right. So now we have tutorial 2, question 8. Done. So I think that the real take-home message is that matrix factorization, so we come back to this point, matrix factorization allow us to cleverly do some of the problems, because if not, then if we try AK brute force, it is very expensive. But if we can break A into PDP minus 1, then suddenly we see that AK, A to the power of K, is a very easy problem to solve. Okay, so I've done question 7 and 8, and then so maybe I will pause for a short time, and then I'll ask you whether you have any questions, and then if not, we can go to question 6 again. Anything? Oh, okay. Right. Let's go to question 6. Actually, question 6 is a very interesting and important question. First, he says, just use pivots and free variables, nothing else. Okay, so he's asking us to only use the most elementary thing that we know about Gaussian eliminations for linear algebra. And then we are given the square matrix A, and we have this AX equals to B. And then he says that there is at least one solution. It means that X exists such that AX will be equals to the right-hand side. And the key is that he's not restricting B. All the B in Rn must have a solution. So he says that I give you the A, I give you the B, and this is n by n, and this is n by 1. So the x must be n by 1, so that this guy becomes n by 1. Any B that I give you, you must be able to solve. Okay. And then, in fact, once you have said that any B that I give you, you must solve, there is actually only one solution. There is only one x. All right. So that's the key idea. Okay. So what can we do? Let's do a simpler one first. Let's say we already know A, and we know that its inverse exists. So by this lecture, you already know what is inverse, because implying A minus 1 equals to I, or A minus 1, A equals to I. The inverse of a matrix is nothing like, it's very similar to a reciprocal of a number. When we multiply something by its reciprocal, we get the identity. The identity, sometimes you put a small n there to say that actually there are n by n elements, all with 0 except the diagonal ones. That's the idea. Okay, so we have Ax equals to B. Now, remember that when we perform Gaussian elimination, we draw this, the A first. And in fact, there's no X, you see. You just draw B immediately. And then you keep on doing this, right? You keep on doing row reduction. And then first you end up with the upper triangle, the pivots, the B. In fact, no more B. It's called B prime because B is also being changed as we are doing. And then there are some numbers here. Remember? Okay. But all this below is 0. So this is Gaussian elimination. But remember, sometimes we, instead of doing Gaussian elimination, we ask you to do Gauss-Jordan elimination. Gauss-Jordan. What does Gauss-Jordan elimination do? It further reduces this matrix from upper triangle. So this is the upper triangle matrix of A. It would reduce to 1. 1. Or for example, let's have only 3, 1. Okay. So I should be very careful here. And then I would have 0 here, 0, 0, 0, 0, 0. And B, let's call this double dash because it again changes. And where is my variable x? So in fact, if you really want to see it, is I, this is identity, right? Multiplied by x1, x2, x3 is equals to B. So B1, B2, B3. The variables of B on the right hand side that has been somewhat change. Okay, I should be very careful. Let's call this B1, B2, B3, but put the double dash on top to say that these are the three elements of B double dash modified through many operations here. Okay, but hey guys, we started with AX equals to B. And now we have IX, the vector, equals to B prime. How did we go from here to here? And we know that if we have AX equals to B, if we left multiply A by A minus 1 on the left, then don't we get A minus 1 AX? Since we multiply on the left hand side, we're going to do exactly here. And therefore, this guy is I. Oops. Okay, we have the I here. Oh, we have the X here. So this guy is this guy. Ah, okay. So now we see again the whole idea that Gaussian elimination, uh, you can also view this as actually multiplying the left matrix of A by A minus 1. So of course, A minus 1 must exist for all these things to take place, but it's the same idea. Okay. So the question now, the big question, of course, is exactly one solution. Why? Because in the Gauss-Jordan, each of the pivot position exists. There are n pivots in this example, 3 by 3, n is 3. And each pivot can be solved for the respective guys. And it is unique because, in fact, the left-hand side is identity. The right-hand side is whatever these values are, and therefore it is unique. Okay, so this is the answer. Clear? Okay. Now, what happens if it's so when would it not be unique? So remember that a solution is unique when all pivots exist. So if you have a 3 by 3, the 3 pivots exist. Now, if only 2 pivots exist and there's one free variable, then you have infinite solution, okay, or no solution. So in this particular example, he says that because I need every B in the right hand side Rn to have a solution, that means all the pivots must exist. Okay, so that's the answer. Now, all right, so I can now go to the second part of the question. The second part of the question says that Ax equals to 0 has only the trivial solution. It means that A multiplied by 0, 0, 0 equals to 0, 0, 0. So this x, the vector, is the trivial solution because anything multiplying by all 0, of course, the right-hand side will be 0. The question is, there are many questions. The first question I ask is, are there any x that is non-zero that such that the right-hand side will be 0? Okay, and yes, there are. And under what condition? So, oops. Okay, question. How do you explain 6a in words? So you say that, explain why the equation has in fact only one solution. You say that when when you perform Gaussian elimination, because this is a square matrix and it has n pivots, therefore there's only a unique solution. To understand why you use this diagram, in the Gauss-Jordan elimination, you're reduced to identity, and in the identity, in fact, when you are trying to solve anything with this identity, you realize that this x1, x2, x3 will be equals to the right-hand side. There's nothing to do. So it's unique. Okay? Now, explain why must have a solution for each b. So in fact, oops, okay, I've got one more question. Thank you. Okay, thank you. So in fact, actually 6b and 6a is very similar. So 6a tells you that each b, 6b tells you right hand side is only the zero, x is the zero solution. Then why we have other solution? In fact, it will be exactly the same. You stop at this figure and you say that if my right hand side is full of zeros, then the only solution that you can get out of this x1, x2, x3, because it's identity minus, sorry, identity multiplied by this guy. Therefore, this vector must be 0, 0, 0. So from that, we answer again. Now, if you go to the invertibility matrix theorem, let me find for you this one. Yep. So the problem is this guy. When he has a trivial solution, it has at least one solution, and in fact, it is a unique solution. And this was what I have used, that A performed to Gauss-Jordan elimination will reach I. And to tell you that it has a unique solution, I say that there was n pivot after reduction. And in the beginning, I use a minus 1 times ax equals to a minus 1 times b to reduce to ix equals to a minus 1 times b to reduce to b double prime. And then here I claim that it is unique. So in the first place, I have used this. So you have to study this invertible matrix theorem, and actually once one of the statement is true, it means all the rest of the statement is true. Okay? All right. Now, so sometimes it's very hard to convince yourself when I explain in words. So I'm going to explain it in a different manner. Let me see. Okay. All right. So I'm going to explain it in this way. So I'm actually doing question 6 again, but I will attack the problem slightly differently. Okay, so let's have a matrix A that is a 2 by 2 matrix. How did I get a 2 by 2 matrix? So first I give you two equations. X plus 2y equals to 3. And then I will reduce to, so I don't like x plus 2y. I want the y to be in one side and the x to be another side. And then I have this equation. So I have 1.5 minus half x. And I plot this line because we like to plot the equations given to us. And then we plot another equation. The second equation given to us is this guy. And then what did I do? So again, we don't like the x and y to be on the left-hand side. We only like y to be on the left-hand side. And we reduce to this guy. And then we reduce to this guy. Half plus half x. So we plot. So remember that I give you two equations. We are having two lines. And then where they intersect, then there's the solution of x and y such that these two equations are true. That's the whole point. I'm given two equations, and then when the two equations intersect, the solution is the intersection point. If they intersect, then the solution exists. If they don't intersect, then the solution does not exist. So in this example, clearly we can see that this is the solution. Okay, so of course, our problem is, if we done it graphically, our problem is over. But how do we do it in linear algebra? Remember, what we do is we start with these two equations and we write the coefficient matrix, which is 1, 2, minus 1, plus 2 for A. And then for B, we have 3 and 1. So you write the coefficient like this. And then here is X and Y and equals, right? So that's the whole approach, right? We identify the equations, we write A, we write the vector X, and we write the vector B, AX equals to B. Okay, so that's what I did in below. So we are here now. And then once we reach this point, we know how to do it in Gaussian elimination because all we do is row reduction. Okay, so we know how two ways to solve for this. We know row reduction, Gaussian elimination, and then we can solve for xy. We also know that if we can do inverse, then the war is over because all we need to do is, again, ax equals to b, a minus 1, ax equals to a minus 1b, therefore x equals to a minus 1b, and we know how to find the inverse of 2 by 2. So here is the refresher. Okay, so I did it for you, and here is the answer. All right, but let us do the row reduction first because in fact, question 6 wanted us to do that. Okay, so what do? We write our augmented matrix here, A. We write our B here, and we start to perform row reduction. So I'm going to introduce this guy, okay? But let's proceed. So what do? Row 2, which is this guy, row 2 is equals to row 2 plus row 1. So it is row 2 is this row 2, the whole thing plus row 1 equals to this guy. So minus 1 plus 1 is 0, 2 plus 2 is 4, 1 plus 3 is 4. So, okay, I've gotten row 2 now. Then I also circle the pivots. And in fact, if we do Gaussian elimination, we are done. Then we can do back substitution. Okay. Now, I promise to talk about this. This equation, R2 equals to R2 plus R1 is represented by E1. Why? What is E1? And how does E1 come into play? Because this matrix on the left is nothing but this matrix on the right, E1, 1, 0, 1, 1, multiplied by 1, 2, 3, minus 1, 2, 1. Correct? You will see that the first row is equals to the first row multiplied by all the elements. The second row is the first row multiplied, this first row multiplied by this guy, plus the second row multiplied by this guy. Okay, so let's do this very carefully. This matrix here, let's call this, maybe let's call this A1 on the left is equals to E1 multiplied by A1. Okay, so go home and do it by yourself. What about here? A2. Okay, A2 is gotten from A1. How did I do this? Well, we say that we don't like this 4 here. We like it to be identity. So what do? We multiply the second row by 1/4. So we reduce 0, 1, 1 because, okay. How do I get this matrix called A2? It is equals to E2 multiplied by A1. Why? You take this guy and you multiply by this matrix and you will get A2. Okay. So you realize that we perform elementary row operations using these E matrices, E1, E2, E3, and the number tell us the order. When did this happen? Okay, what about the last one? So we don't like the 2 now from A2. We will basically row 1 equals to row 1 minus 2 row 2. And then you realize that this is the matrix E3. So A3, the third matrix, is equals to E3 multiplied by A2. That's the idea. So in conclusion, when we start with the matrix A and we end up with the matrix I, we had done this. The matrix I, this one, is equals to this matrix A, this one, multiply by E1 first, then by E2, by E3 on the left. Now, once you have done this, then there's an interesting take home because identity, right? The identity is here. This is A, and therefore these three guys grouped together is A minus 1, the inverse, because that's the property of inverse. The inverse multiplied by A by itself will be identity. Okay, so you can also find the inverse of the matrix using E3 multiplied by E2 multiplied by E1, but it's very painful, of course. As a sanity check, I make sure that I was correct. And then, yep, so it's correct. Using the 2 by 2 is trivial. Okay, but what about B? Remember that I started with this B and I ended up with B prime. Okay, what is B prime? B prime is being operated on all these matrices as well, which is B prime, which is this vector, is original B left multiplied by E1 first, then left multiplied by E2, then left multiplied by E3. Okay, so in fact, of course, again, we remember that this E1, E2, E3 are nothing but the inverse. Oh, okay, so we are back to our original problem, which is here. X is equals to A minus 1 times B. So this A minus 1 times B is this vector here. Okay, I know it's very messy, but I'm going to load this this PDF up, and then you guys can take a closer look. Okay, so that was the whole idea, okay, of understanding it from first principle. I'm going to spend the next 5 minutes to talk about this diagram and when is it unique and when is it not unique. So let's do something interesting first. On the left, I have this matrix, and the obvious thing about this matrix is that the first row and the second row are identical. If you like to see it in row, and if you like to see it in column, the first column and the second column are multiples of each other. Okay. Then we say this is B. Well, to check whether your equation is consistent or not, you should say, let's check the first row and the B. Since the second row is the same as the first row, the B better be the same. Okay, luckily, because otherwise the equation is not consistent and we have no solution. So once we have the A and then we have the B, what do? We will do row reduction to find XY. Now the question is, how many solutions for XY? Then we check. Let's try 1, 1. Plugging X equals to 1, Y equals to 1. So X and Y is equal to 1. Answer is 3, 3. Okay, good. What about X equals to 2, Y equals to half? Also 3, 3. Oops. What about X equals to 3, Y equals to 0? Also 3, 3. So this is a problem, right? The input is different, the output is the same. So that's one way to see. So given different inputs, we project to the same output. of course, most of the question was like, what set of input x, y get projected to 0, 0. So of course, a 0, 0 of x, y will be sent to 0, 0. But what about x equals to -2 and y equals to 1? So -2 times 1 is -2, and 1 times 2 is 2. Therefore, answer is 0. Okay, so in fact, you can find many, infinite of them, such that it all gets to 0, 0. So this is why are there many solutions. And the reason is, one, of course, is that after row reduction, there is only one pivot for two variables. Or you should say there's one free variable. So this free variable causes to have infinite solution. Okay? All right. And once you have this, then of course you can see that the matrix A is not invertible. What about for our case, right? Our case, so this is the last few minutes, I promise you. Our case was this matrix A. And when we solve for question 6A, we realized that every B exists. And the homogeneous solution is only the trivial solution. Why? Okay, let's try. First is 1, 2 equals to 3, and then here equals to 1. We plug in 1, 1, we get 3, 1. We plug in 0, 0, we get 0, 0. There is no other. Every input we send in, we get a unique output. Including the 0, 0 vector, we only get including the trivial solution of x, we get the homogeneous solution 0 vector. So when A is invertible, this very nice property happen, one-to-one mapping. Meaning that if I go from my input to my output, I can map back from my output back to my input. That is why it's invertible, because this guy is the transformation matrix, or sometimes if you prefer, A times the vector x, y is equals to the output. So when you have the output, you can invert back to the input. It's invertible. You look at this guy, it's not invertible. Look at the 0. Many of the inputs can be mapped to 0. Or you look at the 3, 3. Many of the inputs can be mapped to 3, 3. That's why this is not invertible. The output cannot show you what is the input. But if the matrix of the transformation A is invertible, the output will show you exactly who was the input that have converted this. And the reason, of course, is that in row reduction, the number of pivots is all there, and there is no free variable as compared to the previous one when we have one free variable, and that is why we have many of these. Okay, so I think that's it. If you can refresh onto this concept, well, then question 6 will become more obvious. All right, so I'm done. If you have any questions, I think I can still answer some for you. Any? No? If no, then I would edit this and then I will release this in the YouTube very soon. Okay, if you have any problems finding the YouTube, please let me know. Okay, then thank you very much. Bye. Stop recording. Do you want to? Yes.